This lecture is part of a series of lectures for Rad229, MRI Signals and Sequences, offered in the Department of Radiology at Stanford University. The 13th lecture on sampling and timing is divided into two parts. Lecture-13B covers multidimensional sampling and timing. The learning objectives for this lecture are to explain sampling approaches for 3D Cartesian imaging, to describe temporal sampling approaches, to understand strategies for slice interleaving, and to explain principles of multiband sampling and controlled aliasing. When we acquire 3D images, typically using Cartesian imaging, the KY-KZ sampling offers us the freedom to sample in an arbitrary order. There are different approaches, such as centric, where we order the innermost samples first. We can segment into groups based on KY direction, KZ direction, azimuthal angle, or radius, and we can sub-segment groups randomly. These are some examples. This is a sequential KY ordering. KZ, sorry, ordering. This is a sequential KY ordering. And this is a center out ordering. Often we want to consider dynamic imaging applications where we image over time. We might want to resolve motion, such as cardiac motion, joint motion, swallowing, peristalsis, or other effects. This is an image showing the heart beating, where we want to resolve the cardiac motion. We often want contrast enhancement, where we see the uptake of contrast, which is faster in areas such as tumors. We also have functional MRI, where we're studying signal changes in the brain that relate to hemodynamics. A related area is spectroscopic imaging, where we're sampling signal changes due to frequencies over time. In all of these cases, we have to consider spatial and temporal or spatiotemporal resolution. And there's a fundamental trade-off here, simply because it takes time to acquire spatial resolution in MRI. So the top row here shows a desired sampling where we would acquire all of the k-space points at a given time for a given frame. Of course, the actual case is shown below, where each sample is acquired at a different time. So there are options where we can skip samples, and this can reduce resolution or reduce field of view. But there are ways to exploit spatial and temporal information, which we will look at. So this is the desired approach. And of course, these would be very fast frames with high resolution. But in the actual approach, of course, the frame time is much longer. So let's look at a warm-up question. What if we sample the odd, then the even lines during contrast uptake? What will the artifact look like if the signal change is at twice the rate of the frame rate? So the answer here is it will have a bit of an aliased flicker. And this is because if the odd lines and the even lines have a different signal level, that aliased replica will not cancel out properly. So what can we do about it? Well, we could do parallel imaging here, because this would give us 2 times the frame rate. And arguably, if we have calibration information, we can reconstruct the full image from either the odd lines or the even lines. And this would give us true 2x frames. So there are ways to do this that we will look at. So let's think about the spatiotemporal trade-offs, such as field of view. So if we look at the left, if we have a standard full acquisition, these are the frame rates, or the frame times, and they're quite long. You see we only acquire 2 frames. If we do the odd then even lines, what we can often do is take a longer time period to do the sense calibration, and then we can do parallel imaging images as described on the previous slide, where we now have doubled the frame rate. Another approach we often consider with spatiotemporal imaging is what's called view sharing. And here, what we're going to do is divide the K-space into different regions, and typically the central K-space will be called A, and then moving out we'll go to B and C. And what we might do is acquire the A region, followed by some B region, and call that one time frame. And then we're going on the next time frame, we'll again acquire the central information, but instead acquire different outer K-space information in the region C. What we can then do is we can use share across time, or view sharing, which increases what's called the temporal footprint, which is the period over which data is used in a single frame. So we'll often talk about the frame rate being high, but the temporal footprint being lower. So essentially what we have is a little bit of blurring over time in certain spatial frequencies or K-space regions. So there are a number of ways to do view sharing with undersampling patterns, and these are shown here. So going from left to right, we have the tricks approach, which divides K-space up into annular regions. All of these approaches acquire the central information frequently, but in tricks you would acquire different rings of K-space. In the CAIPIR approach, you would acquire different angular regions, or pizza slices perhaps. In the disco or twist approaches, the outer K-space is divided randomly into different regions. And these are similar to the radial golden angle approach, where you will acquire spokes in a seemingly random order so that you can use a subset of spokes. What we can do here is look at the point spread function of a single frame here. So we have incomplete data because we've acquired, in the case on the left, the central K-space, and then a subsample of the outer K-space. And in all of these cases, we have this subsampling. So what you can do is look at the point spread function, and you see that in the tricks approach, the side lobes of this point spread function are the highest of all the approaches. The CAIPIR approach, they're a bit lower. In the disco and twist approach, as well as the radial golden angle approach, the side lobes are much lower and quite incoherent. And we'll see that this can be quite useful later on. So we've already looked at radial imaging in a previous lecture, but let's look again at some of the options when you have radial imaging. So what we can do is we can take a low resolution image from a reduced number of spokes, and this has a full field of view. So this can give us a high frame rate at low spatial resolution. But we can also trade off retrospectively, because what we can do is view share the higher spatial frequency information with the central information. So we can do something like this, where we've divided up these spokes and we acquire the yellow and orange spokes at different time frames. And then we can basically use the inner information from a narrower time window and view share the outer K-space information from both the orange and the yellow here. And this gives us very sharp images with a high frame rate. And the difference between doing this and fully sampling is actually hard to notice, because a lot of the information is at the low spatial frequencies, and that's why it's so important to sample the low spatial frequencies very frequently. Again, in this approach, we can consider the temporal footprint, and the temporal footprint here would be just 2 frames in this example. So let's look at another approach. This is the disco or twist approach. And again, here, what this does is it has an A region, and then it's divided the outer K-space into B1, B2, and B3. So over time, we acquire the center, and then we've randomly divided samples into these B regions. So what we do is that for a specific time frame, we view share over these 3 B regions. And then we do this at the next for the next time frame as well, and the next time frame. So here we can define the temporal resolution, typically as how frequently we sample the central K-space information, and the temporal footprint is basically the full temporal window from which we use samples in the reconstruction. we should note that these techniques are usually combined with parallel imaging. So parallel imaging is already happening in the background typically here. So these random sampling patterns may make you think of compressed sensing MRI. And this is an approach where we take our MRI data, we sample much less data, we sample it randomly, and it turns out that we look at these images, and the image that is the most compressible or sparse tends to be the right result. So this is one point of view on compressed sensing here. But as long as we find the image that is most compressible, which is consistent with the data, this will give us the right result. And this is the constrained reconstruction that's typically used for compressed sensing, where there's sort of two components. One is enforcing sparsity, and one is trying to enforce consistency with the data that were actually sampled. So we can look at this slide, which is a bit of a classic slide now from Michael Lustig. And what you have here are simply three peaks here of different colors. They have three different harmonics in one dimension here. If we take an inverse Fourier transform of this after random sampling, what we have is this sort of incoherent noise-like pattern here. But what happens is we can set some threshold here, and we can basically find the peaks above this threshold, but we know the incoherent shape, and we can suppress the incoherent signal from these, and we'll actually be able to extract the smaller peak as well that looks like it's buried in the noise-like artifact here, because that noise-like artifact is actually not noise. So the combination of the data consistency and regularization or sparsity enforcing reconstruction will allow us to reconstruct the image in most cases here. So then we can hopefully reconstruct something that's pretty similar to what we started with. So these randomized sampling patterns in combination with compressed sensing are very powerful. So we can do things like this, which is like a variable view sharing approach here, where basically we have different undersampling factors here, given by r equals 8, 4, 2, and 1. So r equals 1 here is fully sampled. And this sampling pattern is designed so that when we combine two of the r equals 8 patterns, we still get a fairly even distribution of samples. And this is very similar to the golden angle radial approach that we've seen in a previous lecture here, where the overall sort of angular density of spokes is roughly constant, is uniform over time. So what this means is we can take any temporal window and we can retrospectively trade off by using some temporal window and applying some factor of compressed sensing to reconstruct our image. So a more recent approach for that's especially popular for spatiotemporal imaging is using locally low-rank constraints here, where basically we take a group of pixels over time, and we rearrange this into this matrix, and we basically try to apply, take advantage of the fact that this matrix is locally low rank, and this is a constraint that is very, very effective. It's data-driven, it enforces sparsity, and it allows us to take advantage of a high number of dimensions when we're reconstructing these images. So in order to do this, we need these randomized type acquisitions, which have incoherent artifact, and these are much more successful when you try to suppress this background using these constraints. Okay, so let's switch gears a little bit now. We'll talk about some of the timing considerations for acquisitions, and often we're doing cardiac or respiratory timing with acquisitions for different reasons here. So one of the approaches is called Cine, and here we're exploiting the periodicity of the cardiac or respiratory cycle. And typically this is done with cardiac imaging because typically the cardiac pattern is more periodic than, say, the respiratory cycle. So here what we'll do is we'll sample some number of KY lines repeatedly, and then we'll acquire the next lines on the next heartbeat. And this can give us a very high frame rate and spatial resolution. So it looks like this, where we might acquire 3 lines on one heartbeat and then acquire these repeatedly. And then on the next heartbeat, we'll acquire some of the next lines. Now another approach we'll do here is to start the acquisition based on some kind of an external trigger. This can be an EKG, plethysmograph, or respiratory bellows. So what this does is it times the acquisition so that hopefully the motion state is the same at each point. And then another thing that's related is gating, where we can excite continuously, but we're only acquiring the information after the trigger. Okay, so here we might want to keep the signal in a steady state, but we're not actually acquiring the data during the periods of greater motion. And of course you can combine all of these or any of these techniques in your acquisition. So the different techniques that are used here. So here is a question. So let's look at a question on Cine Acquisition. If the heart rate is 72 beats per minute and we want to acquire a Cine image with 256 by 256 matrix, 5 millisecond TR, and 40 millisecond temporal resolution, how many cardiac cycles are needed? So here we see that for 40 millisecond temporal resolution, we can acquire 8 lines of K-space within each ultimate frame here. So we call this 8 views per segment. That means that we can divide 256 by 8, and that gives us 32 heartbeats to get all of the information. So how many TRs can we place per heartbeat if we use 75% of the cardiac cycle? So here we have 60 seconds divided by 72 beats per minute times 75%, or 5/8 of a second, or 0.625 seconds. If we divide this by the TR, this gives us 125 TRs. So the next question is how many Cine frames do we acquire? And recall that we have 625 milliseconds here divided by a 40 millisecond temporal resolution, and that gives us 15, or basically 125 divided by 8 is 15, because essentially we use the 120 and we throw away the last 5 milliseconds. Okay, so another important topic with timing is slice interleaving. Multi-slice acquisitions are common because these allow efficient volumetric imaging. These acquisitions can be either sequential or interleaved. In sequential acquisitions, you acquire all of the information for one slice, and then you go on to the next slice. Whereas in interleaved imaging, we acquire part of the information for one slice, and then part of the information for the next slice, and so on. The interleaving is time efficient if there is dead time due to a long TR and a short sequence. There are different ways to interleave the slices, and these will reduce saturation of adjacent slices as shown by the profiles at the bottom. So we can do sequential slice interleaving here, where we acquire these sequentially, but in this case we might have interference from adjacent slices. So this could be reduced by using, say, the odd-even approach, where we simply acquire all of the even slices and then all of the odd slices, which gives us sort of a minimum of at least a half a TR of recovery time between adjacent slices. We can also use more sophisticated schemes like this bit reversed order here, which acquires essentially the furthest, maximizes the distance between slices that are acquired next to each other in time. And there are other schemes to do this as well, of course. So another question you have to ask is how many slices can you interleave, or should you interleave? So here we show a TR, and you can see an example where we can essentially fit only 3 slices, because each slice here has a spin echo train, so it takes a certain amount of time to play. So usually when we specify an acquisition, we'll specify the repetition time, the inversion time, the echo train length, and the resolution, and all of these parameters. So what this gives us is the pulse durations, or the sequence time as it's sometimes called, as well as the RF power, or basically the minimum time that you can play the sequence here. So it's sort of the minimum time for between playing the sequence so that the RF power is not too high. And then basically our maximum number of slices that we can interleave is either TR over Tseek or TR over Tmin. Okay, so it depends really on either the pulse duration or the RF power. So often we reduce flip angles so that we're limited by the sequence time rather than the RF power. Then you can also reorder the slices into time slots. So we don't necessarily have to scan the slices in order as shown here. You can put them in arbitrary order and that won't really change things. But if we don't fit them, then we acquire another acquisition for additional slices. So it would be unfortunate here if we have 4 slices because we can only fit 3. So now we're going to have to double our acquisition time just to get that last slice. However, there are ways to do more flexible interleaving. So as I've said, we typically consider the slice number and the phase encode number. So if we look at a color plot here, essentially we're interleaving here 12 slices, and you see that going across the graph here. And what we're going to do is we're going to read off here, and this is basically giving us the slice number that we're imaging. And then across here is giving us the phase encode. So the different colors mean different slices in the top plot and different phase encode numbers on the bottom plot. So in this example, we'll then go through all the slices again for the next phase encode, and so on to get to the end. But notice we've only acquired half of the slices here, and now what we do is we're going to acquire the remaining slices using the same technique here for the other half of the slices. And this works fine as long as the slices, the total number of slices is nicely divided by the number of slices we can fit in the acquisition. However, what if we want to acquire one more slice? Without changing the TR here, that's going to now add a significant amount more time. So one of the things we might consider doing is decoupling the phase encode number from the slice number. So now we can look at this diagram on the right, and essentially what we see here is that as we go across, we're going through the different slices, but for each slice we might play a different phase encode number. Now notice if you instead fill this table out, going down the column first, we have all of the phase encodes for the first slice, and then we simply go on to the next slice and show all of the phase encodes and go into the next column. So we can actually fill this in column first and read it out row first, and this gives us a very easy way to schedule the slices and phase encodes so that we can actually acquire the slices in a minimum amount of time overall. Another interesting idea with interleaving is that of inversion recovery sequences such as FLAIR or STIR. And here what happens is you have an inversion time, TI, and this is dead time where we might not be doing anything. So what we might be able to do is interleave other acquisitions in this time. Now this does place additional constraints on the inversion time and the TR. And if we look at this example here, what you can see by the different colors is we have an inversion, and then let's skip ahead and we see that we image this later on. But before we image that signal here, we can excite another slice, and then in that inversion time, we've interleaved the imaging. So you can sort of see how we've done this here, where we take an inversion and the corresponding imaging, and we've carefully ordered things so that we have other acquisitions, other slices in this time. So a very popular topic over the last decade in MRI has been multiband imaging. And the idea here is we're going to image multiple slices simultaneously. At the simplest level, we can do this by multiplying the RF pulse by a cosine. This will result in a convolution of the RF profile with 2 delta functions, or basically a replication of the slice profile, so it's exciting 2 slices at the same time. Now this does increase the SAR. Now when it comes to the imaging, there are a lot of different ways to do this. We can design this 2-slice scheme so that we excite the slices in a 1-1 or a 1-1 pattern, and then add and subtract these. and this is a Hadamard encoding approach that can be extended to more slices. We could do POMP, or phase offset multiplanar, where we alternate the excitation patterns and we increase the Y field of view, and we're actually able to encode our two slices into the in-plane field of view. We can use parallel imaging, where we use coils to separate the slices. And we can do blipped sequences, which we'll look at a little bit later, where essentially we give you a small slice-dependent phase, and it's essentially like 3D imaging, but with a limited excitation range. And this is actually quite similar to Dixon water-fat imaging, where the slices are like spectral peaks, and they have a different amount of phase between them. So let's look at a question to study the effect of slice-encoding variations here. So if we alternate the sign of the KY data lines, what will happen to this image here? So the answer is we'll have a half field of view shift in Y that looks something like this. Now, if we alternate the sign of the RF pulse, what happens? First, in gradient spoiling, and the answer is again we have a half field of view shift in Y. What happens in RF spoiled sequences? And again we have a half field of view shift in Y, because linear phase just doesn't matter in RF spoiled sequences. And what about in balanced SSFP? So here we have a half field of view shift, but we also have this phase cycling approach that we saw before. And this will result in a shifting of the frequency response of the sequence. However, the main conclusion to draw from this is again that if we modulate the KY data by alternating the sign, we'll do a field of view shift. And more generally, if we modulate the KY by a cosine or a complex exponential, then we'll get an arbitrary shift in the Y direction. So this brings us to the idea of controlled aliasing, which goes by a variety of terms. So we can look at 3D sampling, where we have freedom of our KY and KZ locations. And here we can use what's sometimes called hexagonal or checkerboard sampling, and this will offset replicas that are aliased. And this can reduce aliasing because the replicas are further apart. We can do a multi-slice version of this, where we alternate the phase during the excitation, or we use blips. What happens here is the offset replicas allow you to use the in-plane coil sensitivities to help separate the slices. And this is similar to the POMP approach, but with parallel imaging. You can also think of this as a 3D K-space here. So here is the checkerboard type sampling pattern here. And this is the resulting aliasing pattern that you get from a circular object here. And what you see here is that with this pattern, we've pushed those aliased replicas that if we simply just skipped every second line, these would actually be overlapping. But right now, they're not even overlapping. So this is helpful for doing parallel imaging, because you're more likely to have successful anti-aliasing when the objects that are aliased are further apart, because you're more likely to have a better coil sensitivity difference between those locations. Okay. So let's look at an example with multiband encoding. So if we start here with a 1 kilohertz bandwidth excitation, if we want to excite two slices that are 5 millimeters thick and 2 centimeters apart, first question is, how do we modulate the pulse to excite two slices? And the answer here is that if we look at the 1 kilohertz bandwidth and that maps to 5 millimeters, then essentially we need plus minus 2 kilohertz to get that 2 centimeter spacing between slices. So we've chosen the slice-select gradient to give us the proper slice width, and then from that we need a plus minus 2 kilohertz separation for the slices. So we modulate this with a cosine of 2 pi times 2000 or hertz. So here's a picture of slice 1, here's a picture of slice 2. Now, what is the image if we alternate the excitations using the sequence of cosine, sine, minus cosine, minus sine. So this modulation on successive ky lines. And now we're assuming that the slices are 1 centimeter away from the center, which is exactly what we had above. So in this case, the slices are both shifted by a quarter field of view. So slice 1 is shifted like this, and slice 2 is shifted the other way. So what we can do now is we can combine the images here, and we see that just by doing this, we've shifted the signal in the two slices so that the aliasing is from locations that are further away. And essentially what we can do now is we can encode a field of view. So the question is, what field of view should we encode for 2x parallel imaging if we have two coils along y to separate these images? The answer here is the field of view, including the parallel imaging encoding, has to be large enough to separate the objects. So here you see that if given parallel imaging, we're able to support this field of view as shown here, we can completely separate these objects, and we're completely separating these slices. So this is an example of how multiband encoding is often done here, which is essentially using a 2D CAIPIRINHA approach, or essentially it's POMP with parallel imaging. So to summarize this lecture, we've talked about multidimensional sampling, where we have the KY-KZ order. We have KZ sampling for dynamic imaging. We've discussed view sharing and point spread functions. If we use random and incoherent sampling, then we enable compressed sensing. We've looked at different ways to interleave slices in multi-slice acquisitions, including approaches to optimize the overall scan time, as well as to take advantage of inversion recovery blocks. And then we've looked at simultaneous multi-slice imaging and controlled aliasing, which is often used in conjunction with parallel imaging to simultaneously excite and image different slices.